Have you ever looked at a piece of software and wondered what really makes it fast or slow? Is it just a computer it's running on? Or is there something deeper, something baked right into the code itself? Well, today we're going to crack that puzzle. We're going to learn the hidden language that lets us measure the true speed of our code. Let's jump in.
Okay, so picture this. You've got two different sets of instructions, two algorithms, and they both get you to the exact same result. One might be like the tortoise, slow and steady. The other could be the hare, maybe a bit more complex, but it promises to be super fast. So, how do you know which one is actually better, especially when the race gets really, really long?
To really get to the bottom of this, we need a real-world example. So let's dive into a tale of two algorithms. They're both designed to do the exact same job, calculating something called prefix averages. Now that might sound a little technical, but the idea is actually pretty simple. And the difference in how they do it, well, that's what's so important.
So on one side, we have our tortoise. This is the brute force way. Every single time it needs a new average, it goes all the way back to the starting line and re-adds every single number. It's a lot of repeated work. But on the other side, we've got our hare. This one's a bit smarter. It keeps a running total, so for each new step, it just adds the next number and does a quick calculation. They both get the right answer, but how they get there is completely different.
All right, so how do we prove which one is better? The most obvious thing to do, right? You just grab a stopwatch, you run them both, and you time them. It seems direct, it seems scientific, but as we're about to see, there's a huge problem with just using a stopwatch.
This method is what we call an experimental study. You write the code, you run it with a bunch of different inputs, you measure the time super precisely, and then you plot the results on a graph. I mean, on the surface, this feels foolproof. What could be more direct than just measuring the actual time it takes?
But here's the catch. The stopwatch can lie, or at least it doesn't tell you the whole story. I mean, what if your computer is just way faster than mine? What if the specific data you tested with was just a lucky case for one of the algorithms? To get a truly fair comparison, you'd need the exact same hardware, the same software, everything. And even then, your results might not hold up for a different problem. It's just not a reliable way to judge the algorithm's actual design.
So yeah, it's pretty clear the stopwatch is not the right tool for this job. We need to throw it out and start thinking less like a technician and more like a scientist. We need some kind of universal yardstick, a way to measure the algorithm's core logic that has nothing to do with the computer it's running on.
And that universal yardstick has a name: theoretical analysis. This is where we take a step back from the actual code and we look at the blueprint. It's a way to figure out the efficiency from a high-level description, from the pure logic, without getting bogged down by a specific programming language or a specific machine.
So what's the secret sauce here? It's actually really simple. We stop measuring seconds and we start counting steps. We look at the absolute most basic things an algorithm does, like adding two numbers, comparing if one is bigger than the other, or storing a value. We call each of these a primitive operation.
By counting up all these tiny operations, we can create a mathematical function. This function describes the algorithm's performance where the running time is based on n, the size of our input. So the question changes from how many seconds does it take to, as my input n gets bigger, how many more steps does my algorithm have to take? And this quote just nails the key idea, the growth rate. How the number of steps explodes as the input grows, that's not about the hardware. It's a fundamental, unchangeable property of the algorithm's design. It's basically in its DNA.
Okay, so we've got this really powerful idea of a growth rate, but how do we talk about it? How do we label an algorithm's DNA? For that, we need to learn a little bit of the language that computer scientists use. It's a super powerful shorthand for describing performance, and it's called Big O notation.
The core strategy here is something called asymptotic analysis. Now that's a fancy term for a really simple idea. We don't really care how the algorithm performs on tiny little problems. We care about what happens when the input size n gets huge. We want to know, does it scale gracefully or does it just grind to a halt when n goes from 1,000 to 1,000,000?
And Big O notation is the tool we use to describe exactly that. It gives us an upper bound on that growth rate. Think of it like the algorithm's performance guarantee. In the absolute worst-case scenario, we promise it will perform no worse than this.
And here's the beautiful part, the thing that makes Big O so simple and powerful. When we have a function for our runtime, let's say it's something complicated like 5n squared plus 8n plus 2, we just ignore almost all of it. We drop the constants, we drop the smaller terms,
Why? Because when n gets massive, that n² part is going to dominate everything else so completely that nothing else even matters. So we just say its growth rate is n².
So let's go back to our first algorithm, our tortoise. Because it has a loop running inside another loop, the number of steps it takes grows quadratically. As our input n grows, the work it has to do is proportional to n². So we say its performance is big O of n², or O of n².
And now, what about our second smarter algorithm, the hare? Well, it just has one single loop. The number of steps it performs grows in a straight line, directly proportional to the input size n. So we say it runs in O(n) time. It's linear. And this is where it all clicks. The difference between O of n and O of n² isn't just a gap, it's a massive chasm. For a tiny input of just 10 items, the brute force method takes about 10 times more steps. Okay, annoying, but maybe manageable. But what happens when we scale that up to an input of, say, 1 million? The smart O of n algorithm takes about 1 million steps. The brute force O of n² algorithm, it takes 1 trillion. That difference isn't just big, it's completely and totally insurmounted.
So why do we care so much about this theoretical growth rate? I mean, why is this more important than the actual stopwatch time we could have measured earlier?
Because the crucial point is this. It's not about trying to save a few milliseconds on your laptop. It's about building software that doesn't just fall apart when it goes from 10 users to 10 million users. It's all about being able to predict and guarantee how your software will perform when things get serious.
This table here is like a quick cheat sheet. An O1 or an O log n algorithm is fantastic. It barely even notices as the input grows. On is solid, it's predictable. But once you hit On², performance starts to degrade fast. The goal is always to stay as low on this chart as you possibly can. And this focus on the worst case, it's not just academics being pessimistic, it's absolutely critical for the real world. Think about a video game. You need to guarantee it can keep up even when the screen is filled with explosions and dozens of characters. A momentary freeze, that worst-case scenario, can completely ruin the experience. And that same principle applies to things like high-frequency trading or self-driving cars, where failure is simply not an option.
So I'll leave you with this final thought. Sure, a faster computer can make any program run quicker, no doubt about it. But what it can't do is change the algorithm's DNA. It can't change its growth rate. A faster machine might hide the problem for a little while, but as the scale of the problem gets bigger and bigger, the tortoise with the better algorithm will always eventually lap the hare.